For this lesson, I'm going to go over a brief introduction to working with spatial data types in R. If you're not quite familiar with spatial data, it's generally grouped into two main formats, vector data and raster data. Vector consists of points, lines, and polygons. And raster data you can think of as images. It's a matrix of cells or pixels organized by rows and columns, and each cell or pixel has a value associated with it. Often in working with environmental data, this is things like satellite imagery, climate, land cover, and elevation. So we're going to use two R packages to import vector and raster data. And if we go back to a fresh R session, hopefully you still have the setup script that we saved from lesson 1. If you want to execute an entire script, you can click the source button in RStudio. Otherwise, for the workflow today, I'm just going to open a fresh script. You can also work off of the R Markdown document you created in lesson 1. And for many workflows, you'll start with setup at the beginning of the script. So we can use the source function. And in this case, my setup script is located in a separate folder. I can execute that. I already had it loaded though, however. And so now before we start reading in and importing data, we're going to create a data folder in whatever R project you're working in. This is common that data is organized in a folder by itself. You can create a folder over here in the Files pane by clicking New Folder. But if you want to get used to using the terminal, checking that you're in your root project directory, we can use the make directory function, and we want to add a folder called data. And now we can see that pop up over here. Now we have a folder called data. So starting with the Tigers package, we're going to import some polygon and line shapefiles. For polygons, we're going to import county shapefiles for the state of Colorado. Import Colorado counties with Tigris. And the function for this is relatively simple. Let's call this object counties. And the function to import county shapefiles is counties. And then within it, we tell it which state we want to import counties for. And we're going to use the 2-letter state code. And now it tells us retrieving data for the year 2021. Remember, it's good to always check the default arguments for functions. By default, Tigris will import the most recent data available. If you want any historic data, you would specify the year here. And we'll work a little bit more with this in a second, but we're going to import one more shapefile, and we're going to import roads. But because these line shapefiles are pretty meaty, we're going to confine this to just Larimer County. We'll call this object roads, and this function is also pretty self-explanatory. It is called roads. And now within this, we specify the state and the county. Remember, spelling is important. Okay. Now it tells us it's importing roads, console. And while that is working, throughout today, we're going to be using another new R package called tmap for some quick visualizations. We'll work a lot more with tmap in the geospatial lesson, but we just want to do some quick plotting for all of this spatial data. And with tmap, we can plot in both static and interactive mode. You just have to set the mode, and then every plot you make afterwards will be either static or interactive. So we want to set tmap mode to interactive for this lesson. We do that with tmap_mode. And for interactive, it is view. For static maps, it is plot. And so then it says tmode set to interactive viewing, and now everything you make after that will be an interactive map. Okay, so with tmap, there's a few ways we can make a quick map. Today we're mostly going to be using the QTM function, which stands for Quick Thematic Map. If we do QTM of counties, this interactive map should pop up in your viewer pane, And now we have a map of all of our Colorado County polygons. We can click on it and get some metadata or attributes associated with each polygon. You can also control the layers over here. You can change the base map and turn things on and off. If you wanted to make a more detailed map, instead of using QTM, you can use TM shape and then TM whatever type of spatial object you want to add. So we can basically replicate this map by running TM shape, and we give it the object name. And since this is a polygon, next we tell it what type of layer to add. This is TM polygons. And similar to ggplot, tmap also uses plus signs instead of the pipe. And so this is just 2 lines of code now instead of 1, but it makes the same map. The second method we will use later on is better when you want to create more customized maps. And then if we go back here, say we wanted to plot both, let's say counties and roads. This might take a while because our roads file is a little dense. Now we have an interactive map with both of our layers. We see the counties, and then on top, the lines shapefile of all the roads. Okay, so let's step back a second and let's look at what data type our counties object is. So let's run class of counties. And it returns both data frame and SF. So SF, if you may have noticed, is another R package we installed with our setup script. SF stands for Simple Features. It's a package that provides easy and efficient ways to work with vector data specifically. And it represents spatial features as a data frame or tibble with an additional geometry column. So it allows you to work with tidyverse functions so you can perform manipulations on these spatial objects like you would to a normal data frame. Now, working with point data is sometimes a little different. Often with points, you will have a Excel sheet or CSV with a latitude and longitude column. Now, when you import this to R as a CSV, it is not technically a spatial object yet. It's not an SF object. So now we're going to walk through how you would convert a data frame of coordinates to a spatial object in R. I'm just going to copy this over from the lesson plan for today to make sure I have all the coordinates correct. But here we're just creating our own data frame. And let's say we have these 3 locations along the Pooter Highway. And we have a column for longitude and latitude of each location. Okay, so Pooter points. We want to look at the class of this. It is just a data frame. It has no spatial awareness to it yet. So to convert a non-spatial object to a spatial object with the SF package, the function is st_as_sf. So let's create a new object so we don't overwrite the old one. We'll call it Pooter points SF. So we run st as SF. And the first thing you give it is the non-spatial object you want to convert. Since this is points, we specify the columns that are the coordinates. And it's important to note that you'll always specify longitude before and then latitude. It always goes X and Y format. We concatenate these column names together. Again, they must match that of the data frame we are converting. And third, which I'll get to in a second, is specify the coordinate reference system. And here we are using the code 4326, which you might want to memorize. This is the reference system for WGS84, which is most common, the coordinate reference system used in the US, and often when you're working with coordinate data, when you're using GPS units, etc. All right, so that converted pretty quick. Now if we look at the class of our new Pooter points SF object, now it is a data frame and an SF object. Oops. And if we print out the details here, now instead of looking like a data frame metadata, it tells us it's a simple feature collection. The geometry type is point. It tells us the CRS and then all the attributes tied to it, which in this case is just names. Okay, so that was working with various forms of vector data. Now we're going to work with some raster data. Now we're going to use the elevator package, and this allows us to import raster digital elevation models, or DEM data, from the AWS Open Data Terrain files. And so let's call this object elevation, and the function to get elevation data is get elev raster. So it's going to return elevation as a raster. Now there's various ways you can import this data. One way is to give it a spatial object where it will use that object's bounding box to confine the tile download from. So we're gonna stick to the state of Colorado, and so we can use counties as our spatial bounding box. And then the next thing is the, you have to specify the Z level, which kind of stands for zoom level. This is basically the resolution of the raster you want to return. So a zoom level of Z of 7 is almost equivalent to a 1 kilometer resolution, which is relatively rough resolution, but it will allow us for quick import and analysis throughout this tutorial. Okay, so now we have our elevation data. If we look at it, we see the class is raster layer. It also shows us the resolution. It told us note that units are in meters. So each pixel value of elevation is in meters. And it tells us, again, the CRS, which we'll come back to in a second. If we look at a quick plot of elevation, we see a few things to note first. First is it doesn't really have a very informative name. This long name is actually just a title it gives a temp file. It's importing the data as a temp file, so it only exists in your R session. When you exit out of it, it will disappear. That temp file will be deleted. And second, by default, TMAP categorizes or displays raster data by automatically categorizing it. And there's a way we can switch that to a continuous palette, but here we have to use the TM shape method. So if we do TM shape elevation, and then here we use TM raster. And within this function, we can specify the style to continuous. And then we can also give it a more informative title, and we'll call it elevation in meters. Okay, so this looks a little more cleaner for an elevation raster. Now, a thing to note is that we will be working with the Terra package to deal with raster data throughout this course. Now, Terra has a little quirk that it only deals with this specific type of raster data. When you look back at here, this was a raster layer. So the elevator R package still uses the raster R package to import raster layers. This package will be outdated. There's a lot of things to go into here, but basically we want to stick to the Terra package. So there's one step we have to make here is convert this raster layer to a Terra raster object, which is called a spat raster object. And we can do that really easy. We're going to overwrite the old one. So let's call this elevation, and we can convert it by using the rast function, and it converts it pretty quick. And now when we look at elevation, we see it is a class of spat raster instead of raster layer. And another thing we want to do, we noted this weird file name. If we want to give it a more informative name, we can use the names function. So we want to change the names of elevation, to be, let's just call it elevation. And now if we print out the info of our raster object, now it has name elevation. And now, since it's a Terra object, we can use Terra functions. For example, we see that this raster layer is actually extended outside of the boundary of Colorado. So what we can do is crop it to the bounding box of our counties object with the crop function. Let's call this elevation crop. Now, before we perform any spatial operations, we need to go back to the coordinate reference system, because before you do anything with multiple spatial objects, you need to check that they are in the same CRS, which there's more details on this in the lesson plan, but essentially there's a lot of different ways that spatial data is defined to be projected on Earth, and when you're analyzing data, they need to be in that same projection. So before we crop our layer, we need to check for projection. With the Terra package, we can use the function CRS to check the CRS of both vector and raster data. For checking the CRS of SF objects, we can use STCRS. So say we want to check CRS of our counties, and it'll print a lot of wordy information, but the big one at the top here is that this is an NAD 83. And now if we want to check if two objects are in the same CRS, let's use the Terra function. Let's see, since we're cropping to our counties, we want to see, is the CRS of counties the same as the CRS of elevation? And it returns false. Okay, so this is a sign that we need to first project our data to the same coordinate reference system, and then we can perform our operations. So let's project our raster data to the CRS of counties. So let's call this elevation PRJ for projected. We're going to project elevation to counties. And we get an error. So this is a case where in the first lesson, remember I talked about when you use that double colon. So if we go and try and write this out again, when we start typing project, oops, it's not popping up, but by default, this is actually using the project function from a different package, which is why it's not working. So what we need to specify is from Terra, use that project function. And so now when we do project elevation to counties, it works. There's a warning, but you don't have to worry about that too much. Okay, now we can crop elevation to counties extent. Let's call this elevation crop. Use the function crop, and again we are cropping elevation to the extent. We're using a new function here called ext of our counties object. And now if we do a quick plot of elevation crop, it now is cropped to the extent of Colorado. Okay, finally, I'm going to walk through how to read and write spatial data. So all this data we're working with currently only exists in your R session. But say you want to save either this county shape file or this elevation raster, there's different ways you would do that. To save SF or vector data from the SF package, it's write_sf. And you tell it the name. Let's just save the counties object for this example. And then remember that data folder you made in the beginning. We want to save it within the data folder. Let's call it whatever you want. We'll keep the name counties and save it. When we're working with vector data, it's important that we specify .shp to save it as a shapefile. And then to save raster data, we would use the function write raster. And again, we give it, let's say we want to save elevation crop, and we do the same thing. Specify the file path, data, let's call it elevation. And in this case, the extension is .tiff. There are various different formats of raster data, but geotiff, which the extension is .tiff, is most often the one we'll be working with, so we'll be saving it in that file format. And now I want to make a quick note on our data files. These are files that have the extension .rdata. And this is, instead of saving an actual file, it essentially saves your environmental variable. So the file size is smaller and it's more portable. So sometimes this is an easier way to save data. And with our data files, you can also save more than one object at once. So for example, let's create an R data file. The function is save. And let's save both our counties object and our roads object. So you give it just all the names of the objects you want to save, and then you have to specify file equals. If you just type the file path, it'll throw an error. We have to specify this argument name. So let's save this as data / let's call it spatial objects. And here you have to specify .r D, data. Okay, let's execute that. And let's check our data folder. So now you see spatial objects.r data. And so let's test this. Let's remove these objects from our environment, which you can do with the rm function. Although beware, this function is permanent. If you remove something, it doesn't come back. So let's remove counties and roads from our session. It's quick, and now they're gone. They don't exist anymore. But since we saved it as an R data file, we can use load, and we specify the file path of the R data file with the .r data extension. It might autocomplete. And now we execute this, and we see those objects back in our environment. So it will save them as whatever environmental name they had, and when you load it back in, they will come back in with that same variable name.